Good morning. Today we're going to talk about a new balanced search structure, so a data structure that maintains a dynamic set subject to insertion, deletion, and search, called skip lists. So I'll call this a dynamic search structure because it's a data structure, it supports search, and it's dynamic, meaning insert and delete. So what other dynamic search structures do we know, just for sake of comparison, and to wake everyone up? Shout them out. Good, efficient, I should say. Also good. Logarithmic time per operation. So this is a really easy question to get us off the ground. I've seen them all in the last week, so it shouldn't be so hard. Treep, good. On the problem set we saw treeps. That's in some sense the simplest dynamic search structure you can get from first principles, because all we needed was the bound on a randomly constructed binary search tree, and then treeps did well. So that was sort of the first one you saw, depending on when you did your problem set. What else? Charles?
Red-black tree.
Red-black tree is a good answer. So that was exactly 1 week ago. Hope you still remember them. They have guaranteed log n performance. So this was a expected bound. This was a worst case order log n per operation. Insert, delete, and search. And there was one more. For those who went to recitation on Friday. It's rather in B trees, good. And by B trees, I also include 2, 3 trees, 2, 3, 4 trees, and all those guys. So if B is a constant, or if you implement your B tree nodes a little bit cleverly, then these have guaranteed order log n performance. So worst case order log n. So you should know this. These are all balanced search structures. They're dynamic. They support insertions and deletions. They support searches, finding a given key. And if you don't find the key, you find its predecessor and successor pretty easily in all of these structures. If you want to augment some data structure, you should think about which one of these is easiest to augment, as in Monday's lecture. So the question I want to pose to you is, suppose I gave you all a laptop right now, which would be great. But then I asked you, in order to keep this laptop, you have to implement one of these data structures, let's say within this class hour. Do you think you could do it? How many people think you could do it? One, a couple people, a few people, okay. All front row people, good. I could probably do it. My preference would be B trees. They're sort of the simplest in my mind. This is without using a textbook. This would be a closed book exam. I don't have enough laptops to do it, unfortunately. So B trees are pretty reasonable. Deletion, you have to remember this stealing from the sibling and whatnot. So deletions are a bit tricky. Red-black trees, I can never remember. I'd have to look it up or rederive the 3 cases. Treeps are a bit fancy, so that would be take a little while to remember exactly how those work. You'd have to solve your problem set again if you don't have it memorized. Skip lists, on the other hand, are a data structure you will never forget, and something you can implement within an hour, no problem. I've made this claim a couple times before, and I always felt bad because I'd never actually done it. So this morning, I implemented skip lists, and it took me 10 minutes to implement a linked list and 30 minutes to implement skip lists, and another 30 minutes debugging, but there you go. It can be done. Skip lists are really simple, and at no point writing the code did I have to think. Whereas every other structure, I would have to think. There was one moment when I thought, how do I flip a coin? Okay, that was the entire amount of thinking. So skip lists are a randomized structure. Let's add in another adjective here. And let's also add in simple. Okay, really cluttered. So we have a simple, efficient, dynamic, randomized search structure. All those things together. So it's sort of like treeps in that the bound is only a randomized bound. But today we're going to see a much stronger bound than an expectation bound. So in particular, skip lists will run in order log n expected time. So the running time for each operation will be order log n in expectation. But we're going to prove a much stronger result, that they're order log n with high probability. So this is a very strong claim. And it means that the running time of each operation, the running time of every operation is order log n almost always, in a certain sense. Why don't I foreshadow that? So it's something like the probability that it's order log n is at least 1 minus 1 over some polynomial in n. And you get to set the polynomial however large you like. So what this basically means is that almost all the time, you take your skip list, you do a polynomial number of operations on it, because presumably you're running a polynomial time algorithm that's using this data structure. You do polynomial numbers of inserts, deletes, searches. Every single one of them will take order log n time. Almost guaranteed. So this is a really strong bound on the tail of the distribution. The mean is order log n. That's not so exciting. But in fact, almost all of the weight of this probability distribution is right around log n. Just tiny little epsilons, very, very tiny probabilities you could be bigger than log n. So that's where we're going. This is a data structure by Puig in 1989. So this is the most recent. Actually, no, sorry. Treeps are more recent. They were like 93 or so. But a fairly recent data structure for just insert, delete, search. And it's very simple. You can derive it if you don't know anything about data structures. Well, almost nothing. Now, analyzing that the performance is log n, that, of course, takes our sophistication. But the data structure itself is very simple. We're going to start from scratch. Suppose you don't know what a red-black tree is. You don't know what a B tree is. Suppose you don't even know what a tree is. What is the simplest data structure for storing a bunch of items? For storing a dynamic set? A list. Good. A linked list. Now, I'm going to suppose that it's a sorted linked list, so I'm going to be a little bit fancier there. So if you have a linked list of items, here it is. Maybe we'll make it doubly linked just for kicks. How long does it take to search in a sorted linked list? Log n is one answer. N is the other answer. Which one's right? N is the right answer. So even though it's sorted, we can't do binary search because we don't have random access into a linked list. So I suppose that I'm only given a pointer to the head. Otherwise, I'm assuming that it's an array. If it's a sorted array, you can search in log n. Sorted linked list, you still got to scan through the darn thing. So theta n worst case search. Not so good. But if we just try to improve it a little bit, we will discover skip lists automatically. So this is our starting point. Sorted linked list, theta n time. And I'm not going to think too much about insertions and deletions for the moment. Let's just get search better, and then we'll worry about updates. Updates are where randomization will come in. Search, pretty easy idea. So how could we make a linked list better? Suppose all we know about are linked lists. What could I do to make it faster? This is where you need a little bit of innovation, some creativity. More links, that's a good idea. So I could try maybe, I don't know, add pointers to go a couple steps ahead. You know, if I had log n pointers, I could do all powers of 2 ahead. That's a pretty good search structure, and some people use that in various, like some peer-to-peer networks use that idea. But that's a little too fancy for me, yeah.
You give each node 2 pointers, the 2 nodes that you might want if you're doing a binary search.
Ah, good. You could try to build a tree on this linear structure. That's essentially where we're going. So you could try to put pointers to maybe like the middle of the list from the root. So you search between either here. You point to the median, so you can compare against the median and know whether you should go in the first half or the second half. That's definitely on the right track. Also a bit too sophisticated. Another list, yes. Yes, good. So we're going to use two lists. That's sort of the next simplest thing you could do. Okay, and as you suggested, we could maybe have pointers between them. So maybe we have some elements down here, some of the elements up here. We want to have pointers between the lists. Okay, it gets a little bit crazy in how exactly you might do that, but somehow this feels good. So this is one linked list, L1. This is another linked list, L2. And to give you some inspiration, I want to give you, so let's play a game. Game is, what is this sequence? So, sequence is 14. If you know the answer, shout it out. Anyone yet? Okay, it's tricky. It's a bit of a small class, so I hope someone knows the answer. How many TAs know the answer? Just a couple. If you're looking at the slides, probably you know the answer. That's cheating. Okay, I'll give you a hint. It is not a mathematical sequence. This is a real-life sequence. Yeah.
Are they able to stop on one of the subways?
Yeah. In what city? New York. Yeah. This is the 7th Avenue line in New York City. It's my favorite subway line in New York. But what's a cool feature of the New York City subway? It's a skip list. Good answer. Indeed it is. If you want to experience, see, skip lists are so practical. They've been implemented in the subway system. How cool is that? Okay. Boston subway is pretty cool because it's the oldest subway definitely in the United States, maybe in the world. New York is close, and it has other nice features like it's open 24 hours. That's a definite plus. But it also has this feature of express lines. So it's a bit of an abstraction, but the 7th Avenue line has essentially two kinds of cars. These are street numbers, by the way. This is, Penn Station, Times Square, and so on. Okay, so there are essentially two lines. There's the express line, which goes 14 to 34 to 42 to 72 to 96. And then there's the local line, which stops at every stop. And they accomplish this with 4 sets of tracks. So the express lines have their own dedicated track. If you want to go to stop 59 from, let's say, Penn Station, well, let's say from Lower West Side, you get on the express line, you jump to 42 pretty quickly, and then you switch over to the local line and go on to 59 or wherever I said I was going. Okay, so this is express and local lines, and we can represent that with a couple of lists. We have one list, we have one list on the bottom, so leave some space up here. This is the local line, L2, 34, 42, 50, 59, 66, 72, 79, and so on. And then we have the express line on top, which only stops at 14, 34, 42, 72, and so on. Okay, I'm not going to redraw the whole list. You get the idea. And so what we're going to do is put links between the local and express lines, wherever they happen to meet. And that's our two-linked list structure. So that's what I actually meant when I was trying to draw some picture. Now this has a property that in one list, the bottom list, every element occurs. In the top list just copies some of those elements, and we're going to preserve that property. So L2 stores all the elements. And L1 stores some subset. And it's still open which ones we should store. That's the one thing we need to think about. But our inspiration is from the New York subway system. Okay, there. That's the idea. Of course, we're also going to use more than two lists. But, okay. We also have links, let's say links between equal keys. In L1 and L2. Good. So just for the sake of completeness, and because we'll need this later, let's talk about searches before we worry about how these lists are actually constructed. Of course, I wanted that board. So if you want to search for an element, X, what do? Well, this is the taking the subway algorithm. Okay, and suppose you always start in the upper left corner of the subway system. So you're always in the lower west side of 14th Street, and, or I don't know exactly where that is, but more or less, somewhere down the bottom of Manhattan. And you want to go to a particular station like 59, well, you stay on the express line as long as you can, because it happens that we started on the express line. And then you go down, and then you take the local line the rest of the way. That's clearly the right thing to do if you always start in the top left corner. So I'm going to write that down as some kind of algorithm, because we'll be generalizing it. It's pretty obvious at this point. Will remain obvious, but... So I want to walk right in the top list until that would go too far. So you imagine giving someone directions on the subway system they've never been on. So you say, okay, you start at 14th, take the express line, and when you get to 72nd, you've gone too far. Go back one, then go down to the local line. So really annoying directions. But this is what an algorithm has to do, because it's never taken the subway before. So it's gonna check. So let's do it here. So suppose I'm aiming for 59. So I start at 14. Say, okay, first thing I do is go to 34. Then from there I go to 42. Still good because 59 is bigger than 42. I go right again. I say, oops, 72 is too big. That was too far. So I go back to where I just was, then I go down, and then I keep going right until I find the element that I want or discover that it's not in the bottom list, because bottom list has everyone. So that's the algorithm. Stop when going right would go too far, and you discover that with a comparison. Then you walk down to L2, and then you walk right in L2. Until you find X, or you find something greater than X, in which case X is definitely not in your list, and you found the predecessor and successor, which may be your goal. If you didn't find where X was, you should find where it would go if it were there, because then maybe you could insert there. But we're going to use this algorithm in insertion. Okay, but that's search. Pretty easy at this point. Now, what we haven't discussed is how fast this search algorithm is. And it depends, of course, which elements we're going to store in L1. Which subset of elements should go in L1? Now, in a subway system, you probably put all the popular stations in L1. But here we want worst case performance. So we don't have some probability distribution on the nodes. We just like every node to be accessed sort of as quickly as possible, uniformly. So we want to minimize the maximum time over all queries. So any ideas on what we should do with L1? Should I put all the nodes of L1 in the beginning? Okay, it's some strict subset. Suppose I told you what the size of L1 was. I can tell you I can afford to build this many express stops. How should you distribute them among the elements of L2? Uniformly. Good. So what nodes, what keys, let's say, go in L1? Well, definitely the best thing to do is to spread them out uniformly. Okay, which is definitely not what the 7th Avenue line looks like, but let's imagine we can re-engineer everything. So we're going to try and space these things out a little bit more. So 34 and 42nd are way too close. We'll take a few more stops. And now we can start to analyze things, okay, as a function of the length of L1. So the cost of a search is now roughly, so I want a function of the length of L1 and the length of L2, which is all of the elements, n. What is the cost of a search if I spread out all the elements in L1 uniformly? Yeah.
Total number of elements in the length of one plus the division between.
Right, the total number of elements in the top list plus the division between the bottom and the top. So this, I'll write the length of L1 plus the length of L2 divided by the length of L1. Okay, this is roughly, there's maybe a +1 or so here. Because in the worst case, I have to search through all of L1, because the station I could be looking for could be the max. Okay, and maybe I'm not lucky and the max is not on the express line, so then I have to go down to the local line. And how many stops will I have to go on the local line? Well, L1 just evenly partitions L2. So this is the number of consecutive stations between two express stops. So I take the express possibly this long, and then I take the local possibly this long. So this is, say, in L1, and this is in L2. And there's plus a constant, for example, walking down. But that's basically the number of nodes that I visit. So I'd like to minimize this function. Now, L2, I'm going to call that n, because that's the total number of elements. L1, I get to choose to be whatever I want. So let's go over here. So I want to minimize L1 plus n over L1. And I get to choose L1. Now I could differentiate this, set it to 0, and go crazy. Or I could realize that that's not hard, but that's a little bit too fancy for me. So I could say, well, this is clearly best when L1 is small. And this is clearly best when L1 is large. So there's a trade-off there. And the trade-off will be roughly minimized up to constant factors when these two terms are equal. That's when I have pretty good balance between the two ends of the trade-off. So this is up to constant factors. I can let L1 equal n over L1. Okay, because at most I'm losing a factor of 2 there when they happen to be equal. So now I just solve this. This is really easy. This is L1 squared equals n. So L1 is the square root of n. Okay. So the cost that I'm getting over here, L1 plus L2 over L1, this is square root of n plus n over root n, which is, again, root n. So I get 2 root n. So search cost. And I'm caring about the constant here because it will matter in a moment. 2 square root of n. I'm not caring about the additive constant, but the multiplicative constant I care about. Okay. That seems good. We started with a linked list that searched in n time, theta n time per operation. Now we have 2 linked lists searched in theta root n time. Seems pretty good. This is what the structure looks like. We have root n guys here. This is in the local line. And we have one express stop which represents that. Then we have another root n values in the local line, and we have one express stop that represents that, and these two are linked, and so on. Wow. Should put some dots in there. Okay, so each of these chunks has length root n, and the number of representatives up here is square root of n. The number of express stops is square root of n. So clearly things are balanced now. I search for at most square root of n up here, then I search in one of these lists for at most square root of n. So every search takes at most 2 root n. Cool. What should we do next? Let's again ignore insertions and deletions. I want to make searches faster because square root of n is not so hot, as we know. Sorry? More lines. Let's add a super express line. Let's add or another linked list. Okay? This was 2. Why not do 3? So we started with a sorted linked list. Then we went to 2. This gave us 2 square root of n. Now I want 3 sorted linked lists. Didn't pluralize here. Any guesses what the running time might be? This is just guesswork, don't think. From 2 square root of n, you would go to? Sorry? 2 square root of 2 fourth root of n, that's on the right track. Both the constant and the root change, but not quite so fancily. 3 times the cube root, good. Intuition is very helpful here. Doesn't matter what the right answer is. Use your intuition. Now, you can prove that. It's not so hard. You now have 3 lists, and what you want to balance are the length of the top list, the ratio between the top 2 lists, and the ratio between the bottom 2 lists. So you want these 3 to multiply out to n, because that, I mean, the top times the ratio, that has to equal n. And so that's where you get the cube root of n. Each of these should be equal, so you set them, because the cost is the sum of those 3 things. So you set each of them to cube root of n, and there are 3 of them. Okay, check it at home if you want to be more sure. Okay. Obviously, we want a few more, so let's think about k sorted lists. K sorted list will be k times the kth root of n. Probably guessed that by now. So what should we set k to? I don't want the exact minimum. What's a good value for k? Should I set it to n? N is kind of nice because nth root of n is just 1. But that's n. So this is why I cared about the lead constant, because it's going to grow as I add more lists. What's the biggest reasonable value of k that I could use? Log n. because I have a k out there. I certainly don't want to use more than log n. So log n times the log nth root, and this is a little hard to draw, of n. Now, what is the log nth root of n? That's what you're all thinking about. What is the log nth root of n minus 2? It's one of these good questions whose answer is? Oh, man. Remember the definition of a root? Okay, the root is n to the 1 over log n. Okay, good. Remember the definition of having a power? A to the b is like 2 to the power b log a. Sound familiar? So this is 2 to the log n over log n, which is, hope you can get it at this point, 2. Wow. So log nth root of n minus 2 is 0, my favorite answer. Okay? This is 2, so this whole thing is 2 log n. Pretty nifty. So you could be a little fancier and tweak this a little bit, but 2 log n is plenty good for me. Clearly don't want to use any more lists, but log n list sounds pretty good. I get now logarithmic search time. Let's check. I mean, we sort of did this all intuitively. Let's draw what the list looks like, but it'll work. So I'm going to redraw this example because you have to also. So let's redesign the New York City subway system. And I want you to leave 3 blank lines up here. So I should have this memorized by now, but I don't. So we're not allowed to change the local line, though it would be nice. Add a few more stops there. Okay, we can stop at 79th Street, that's enough. So now, we have log n lists, and here log n is about 4. So I want to make a bunch of lists here. In particular, 14 will appear in all of them. So why don't I draw those in? And the question is, which elements go in here? So I have log n lists, and my goal is to balance the number of items up here, and the ratio between these 2 lists, and the ratio between these 2 lists, and the ratio between these 2 lists. I want all those things to be balanced. There are log n of them, so their product, the product of all those ratios better be n, the number of elements down here. So the product of all these ratios is n. How big is, and there's log n of them, how big is each ratio? So call the ratio r. Ratio is r. I should have r to the power log n equals n. What's r? What's r minus 2? 0. Okay, this should be 2 to the power log n. So if the ratio between the number of elements here and here is 2 all the way down, then I will have n elements at the bottom, which is what I want. So in other words, I want half the elements here, a quarter of the elements here, an eighth of the elements here, and so on. So I'm going to take half of the elements, evenly spaced out. 34th, 50th, 66th, 79th, and so on. So this is our new semi-express line. Not terribly fast, but you save a factor of 2 for going up there. And when you're done, you go down and you walk at most 1 step and you find what you're looking for. Okay, and then we do the same thing over and over and over until we run out of elements. Oops, can't read my own writing. 79th. If I had a bigger example, I'd need more levels. But this is just barely enough. Let's say 2 elements is where I stop. So this looks good. Does this look like a structure you've seen before at all? Vaguely? Yes? A tree, yes. Looks a lot like a binary tree. I'll just leave it at that. In your problem set, you'll understand why skip lists are really like trees. But it's more or less a tree, you know. Let's say at this level, it looks sort of like binary search. You look at 14, you look at 50, and therefore you decide whether you're in the left half or the right half. And that's sort of like a tree. I mean, it's not quite a tree because we have this element repeated all over. But more or less, this is a tree, binary tree. At depth I, we have 2 to the I nodes, just like a tree, just like a balanced tree. I'm going to call this structure an ideal skip list. And if all we're doing are searches, ideal skip lists are pretty good. Maybe in practice not quite as good as a binary search tree, but up to constant factors, just as good. So for example, I mean, we can generalize search. Just check that it's log n. So the search procedure is you start at the top left. So let's say we're looking for 72. You start at the top left. 14 is smaller than 72, so I try to go right. Oh, 79 is too big. So I follow this arrow, but I say, oops, that's too much. So instead I go down. 14 still. I go to the right. Oh, 50, that's still smaller than 72. Okay. I try to go right again. Oh, 79, that's too big. So that's no good. So I go down. So I get 50. I go try the same thing over and over. I try to go to the right. Oh, 66, that's okay. Try to go to the right. Oh, 79, that's too big. So I go down. Now I go to the right, and oh, 72, done. Okay, otherwise I'd go too far and try to go down and say, oops, element must not be there. Very simple search algorithm. Same as here, except just remove L1 and L2. Go right until that would go too far, then go down. Then go right until that would go too far, then go down. You might have to do this log n times. In each level, you're clearly only walking a couple of steps because the ratio between these two sizes is only 2. So this will cost 2 log n for search. Good. So, I mean, that was to check because we were using intuition over here. A little bit shaky. So this is an ideal skip list. We have to support insertions and deletions. As soon as we do an insert or delete, there's no way we're going to maintain this structure. It's a bit too special. There's only one of these where the everything is perfectly spaced out and everything is beautiful. So we can't do that. We're going to maintain roughly this structure as best we can. And if any one of you knows someone in New York City subway planning, you can tell them this. All right, so skip list. So this is the real, I mean, this is basically our data structure. You could use this as a starting point, but then you start using skip lists. And we need to somehow implement insertions and deletions and maintain roughly this structure well enough that the search still costs order log n time. So let's focus on insertions. If we do insertions right, it turns out deletions are really trivial. And again, this is all from first principles. We're not allowed to use anything fancy. But it would be nice if we used some good chalk. This one looks a little better. So suppose you want to insert an element x. We said how to search for an element, so how do we insert it? Well, first thing we should do is figure out where it goes, so we search for x. So we call search of x to find where x fits in the bottom list, not just any list. Pretty easy to find out where it fits in the top list. That takes like constant time. But we want to know, because the top list has constant length, we want to know where x goes in the bottom list. So let's say we want to insert 80. We search for 80, we get to, 80 was a bit too big. Search for 75. So we'll find that 75 fits right here between 72 and 79 using the same path. Okay, if it's there already, we complain. And because I'm going to assume all keys are distinct for now, just so the pictures stay simple. But this works fine even if you're inserting the same key over and over. So that seems good. One thing we should clearly do is insert x into the bottom list. We now know where it fits. It should go there. Because we want to maintain this invariant, that the bottom list contains all the elements. So there we go. We've maintained the invariant. Bottom list contains all the elements. So we search for 75. We say, oh, 75 goes here, and we just sort of link in 75. You know how to do a linked list, I hope. Just erase that pointer. And that's all the work in implementing skip lists is the linked list manipulation. Is that enough? No. It will be fine for now, because now there's only a chain of length 3 here that you'd have to walk over if you're looking for something in this range. But if I just keep inserting, 75, then 76, then 76 plus epsilon, and 76 plus 2 epsilon, and so on, just pack a whole bunch of elements in here, this chain will get really long. Now suddenly things are not so balanced. If I do a search, I'll pay an arbitrarily long amount of time here to search for someone. If I insert k things, it'll take k time. I want it to stay log n. If I only insert log n items, it's sort of okay for now. But what I want to do is decide which of these lists contains 75. So clearly it goes in the bottom. Every element goes in the bottom. Should it go up a level? Maybe. Depends. Not clear yet. If I insert a few items here, definitely some of them should go in the next level. Should they go in the 2 levels up? Well, maybe, but even less likely. So what should I do? Yeah.
What if based on the small number of elements, you just keep an ideal partition size from your smallest partition, and you receive that, and you do a split?
Right, so you maintain the ideal partition size, which may be like the length of this chain. And you see, well, if that gets too long, then I should split it in the middle, promote that guy up to the next level, and do the same thing up here. If this chain gets too long between 2 consecutive next level express stops, then I'll promote the middle guy. And that's what you'll do in your problem set. That's too fancy for me. I don't need no stinking counters. What else could I do? I could try to maintain the ideal skip list structure. That will be too expensive. I could say, well, 75 now is the guy that gets promoted, and this guy gets demoted all the way down, but that'll propagate everything to the right, and that could cost linear time per update. Other idea? If I only want half of them to go up, I could flip a coin. Good idea. All right, for that, I will give you a quarter. I think it's a quarter. Yeah. Oh, it's a good one. It's the old line state, Maryland. There you go. However, you have to perform some services for that quarter. Namely, flip the coin. Can you flip a coin? Good. All right. What'd you get? Tails. Okay. That's the first random bit. Okay. What we're going to do is build a skip list. Maybe I should tell you how first. Okay, but the idea is flip a coin. If it's heads, if it's heads, we will promote it to the next level and flip again. So this is in answer to the question, which other lists should store X? how many other lists should we add x to? Well, the algorithm is flip a coin, and if it comes out heads, then promote x to the next level up. And flip again. Okay, that's key because we might want this element to go arbitrarily high. But for starters, we flip a coin. Does it go up to the next level? Well, we'd like it to go up to the next level with probability 1/2 because we want the ratio between these two sizes to be 1/2, or sorry, 2, depending which way you take the ratio. So I want roughly half the elements up here. So I flip a coin. If it comes up heads, I go up here. This is a fair coin. So I want it 50-50. Okay, then how many elements should that element go up to the next level up? Well, with 50% probability again. So I flip another coin. If it comes up heads, I'll go up another level, and that will maintain the approximate ratio between these two guys as being 2. The expected ratio will definitely be 2. And so on all the way up. If I go up to the top and I flip a coin and it comes up heads, I'll make another level. Okay, this is the insertion algorithm. Dead simple. Okay, the fancier one you'll see on your problem set. So let's do it. Okay, I also need someone to generate random numbers. Who can generate random numbers? Pseudo-random. I'll give you a quarter. I have more in here. Yeah, here we go. That's a boring quarter. Who would like to generate random numbers? Someone volunteering someone else. That's a good way to do it. Here you go. You get a quarter, but you're not allowed to flip it. No randomness for you. Well, okay, you can generate bits and then compute a number. So give me a number.
44.
44, good answer. Okay, we already flipped the coin, and I got tails. Whew, done. Okay, that's the insertion algorithm. I'm going to make some more space, actually. Put it way down here. Okay, so 44 does not get promoted because we got a tails. So give me another number. 9. 9, okay. I searched for 9 in this list. Oh, I should mention one other thing, sorry. I need a small change. This is just to make sure searches still work. So the worry is, suppose I insert something bigger and then I promote it. Okay, this would look very bad for a skip list data structure because I always want to start in the top left, and now there's no top left. So just minor change, 9. Just let me remember that. Minor change is that I'm going to store a special value, -infinity, in every list. That will make sure, so -infinity always gets promoted all the way to the top, whatever the top happens to be now. So initially, that way I'll always have a top left. Sorry, I forgot to mention that. So initially I'll have just -infinity, then I insert 44, I say, okay, 44 goes there, no promotion, done. Now we're going to insert 9. 9 goes here. So, -infinity to 9. Flip your coin. Heads. Oh. Did he actually flip it? Just checking. Okay, good. Oh, you flipped it before? Yeah, sure. Okay, you're just giving me a hard time. So we have 9 up here. We need to maintain this -infinity just to make sure it gets promoted along with everything else. So that looks like a nice skip list. Flip it again. Tails, good. Okay, so perfect. This looks like an ideal skip list. Isn't it great? It works every time. Okay, give me another number. 26. Okay, so I search for 26. 26 goes here. Clearly goes in the bottom list. So here we go, 26. And then I erased 44. Flip. Tails. Oh, okay. Another number. 15? 50. Oh, big one. So I search. It costs me a little while to search. I get over here. 50. Flip. Heads. Good. So 50 gets promoted. Flip again. Tails. Okay, looks still reasonable. Another number. 12. It takes a little while to get exciting here. Okay, 12 goes here between 9 and 26. Give me a hard time here. Okay. Flip. Heads. Okay, 12 gets promoted. Now, you have to work a little bit, but we just came here to search for 12. So we know that 9 was the last point we went down. So we promote 12. It gets inserted up here. We're just inserting into this particular linked list. Nothing fancy. We link the two 12s together. Well, it still looks kind of like a linked list. Flip again. Okay, tails. Another number. 37. Jeez. It's a good test of memory. 37, what was it? 44 and 50? And 50 was at the next level up. I think I should just keep appending elements and have you flip coins. Okay, we just inserted 37. Flip. Tails. That's getting to be a long chain. That looks a bit worrisome. Okay. Give me another number. Larger than 50. No, what? Sorry? 51. Good answer. Thank you. Okay, flip again. Heads. Good. And again. Tails. Oh, boy. Another number. Maybe someone else should pick a number. It's not working. What did you say? 52. Oh, good answer. Flip. Tails. Not surprising. We've gotten a lot of heads there. Okay, another number. 53. Thank you. Flip. Heads. Okay, good. Heads. Heads. You didn't flip. All right. 53. You get the idea, right? If you get two consecutive heads, then the guy goes up 2 levels. Okay, now flip for real. Heads. Aha. Finally. Heads we've been waiting for. If you flip 3 heads in a row, you go up 3 levels. Each time we keep promoting minus infinity. Flip again. Heads. Oh my God. Where were they before? Flip again. It better be tails this time. Tails. Good. Okay, you get the idea. Eventually you run out of board space. Now, it's pretty rare that you go too high. What's the probability that you go higher than log n? Another easy log computation. Each time I have a 50% probability of going up, 1 in n probability of going up log n levels. Because a half to the power log n is 1 out of n. So, it depends on n, but I'm not going to go too high. And intuitively, this is, not so bad. So these are skip lists. You have the ratios right in expectation, which is a pretty weak statement. Because it doesn't say anything about the lengths of these chains. But intuitively, it's pretty good. Let's say pretty good on average. So I had two semi-random processes going on here. One was picking the numbers, and that I don't want to assume anything about. The numbers could be adversarial, it could be sequential, it could be reverse sorted, could be random, I don't know. Okay, so it didn't matter what he said. At least it shouldn't matter. It matters here. Don't worry. You're still loved, you still get your 25 cents. But what the algorithm cares about is the outcomes of these coins. And the probability, the statement that this data structure is fast with high probability is only about the random coins, right? It doesn't matter what the adversary chooses for numbers, as long as those coins are random and the adversary doesn't know the coins, doesn't know the outcomes of the coins. So in that case, on average, over all of the coin flips, should be okay. But the claim is not just that it's pretty good on average, but it's really, really good almost always. Okay, with really high probability, it's log n. So for example, with probability 1 minus 1 over n, it's order log n. With probability 1 minus 1 over n squared, it's log n. Probability 1 minus 1 over n to the 100th, it's order log n. All those statements are true for any value of 100. So that's where we're going. Okay, I should mention delete too. How do you delete in a skip list? Find the element, you delete it all the way. Done. That's delete. There's nothing fancy with delete. Because we have all these independent random choices, all of these elements are sort of independent from each other. We don't really care. So delete an element, just throw it away. The tricky part is insertion. When I insert an element, I'm just going to randomly see how high it should go. With probability 1 over 2 to the I, it will go to height I. Good. That's my time. I've been having too much fun here. Got to go a little bit faster. Okay. So here's the theorem. Let's see exactly what we're proving first. With high probability, this is a formal notion, which I will define in a second. Say, every search in n element skip list costs order log n. So that's the theorem. Now I need to define with high probability. So with high probability. And it's a bit of a long phrase, so often we will, and you can abbreviate it WHP. So if I have a random event, and the random event here is that every search in an n-element skip list costs order log n, I want to know what it means for that event to occur with high probability. So this is the definition. So the statement is that for any alpha greater than or equal to 1, there is a suitable choice of constants for which the event E occurs with this probability I keep mentioning. So probability at least 1 minus order 1 over n to the alpha. So this is a bit imprecise, but it will suffice for our purposes. If you want the really formal definition, you can read the lecture notes. There are special lecture notes for this lecture on the Stellar site. And there's the PowerPoint notes on the SMA site. But this is right. There's a bit of a subtlety in the choice of constants here. There's the choice of this constant, and there's the choice of this constant. And these are related. And there's alpha, which we get to set to whatever we want. But the bottom line is, we get to choose what probability we want this to be true. If I want it to be true with probability 1 minus 1 over n to the 100, I can do that. I just set alpha to 100, and up to this little constant, but that's going to grow much slower than n to the alpha. I get the error probability, so this thing is called the error probability. The probability that I fail is polynomially small for any polynomial I want. Now, it's with the same data structure, right? I fix a data structure, it doesn't depend on alpha. Anything you want, any alpha value you want, this data structure will take order log n time. Now, this constant will depend on alpha. So, you want error probability 1 over n to the 100 is probably going to be like 100 log n. That's still log n. Okay, this is a very strong claim about the tail of the distribution of the running time of search. Very strong. Let me give you an idea how strong it is. How many people know what Boole's inequality is? How many people know what the union bound is in probability? Uh-oh. You should. It's in Appendix C. Maybe you'll know it by the theorem. It's good to know it by name. It's sort of like linearity of expectations. It's a lot easier to communicate to someone. Linearity of expectations instead of saying, you know, that thing where you sum up all the expectations of things and that's the expectation of the sum. You know. A lot easier to say linearity of expectation. So, let me quiz you in a different way. So if I take a bunch of events and I take their union, this is sort of either this happens or so on. So this is the inclusive or of k events. And instead I look at the sum of the probabilities of those events. Okay, easy question. Are these equal? No, unless they're independent. But can I say anything about them? Any relation? Smaller. Yeah. This is less than or equal to that. Okay, this should be intuitive to you from a probability point of view. You can look at the textbook. Okay, very basic result. Okay, trivial result almost. What does this tell us? Well, suppose that EI is some kind of error event. We don't want it to happen. Okay, and suppose, so I've mixed some letters here. Suppose I have a bunch of events which occur with high probability. Okay, call those EI complement. So suppose, so this is the end of that statement. EI complement occurs with high probability. Okay, so then the probability of EI is very small, polynomially small. 1 over n to the alpha for any alpha I want. Now suppose I take a whole bunch of these events, and let's say that k is polynomial in n. So I take a bunch of events which I'd like to happen. They all occur with high probability. There's only polynomially many of them. So let's say, let me give this constant a name. Let's call it c. Let's say I take n to the c such events. Well, what's the probability that all of those events occur together? Because they should, most of the time, occur together. Because each one occurs most of the time, occurs with high probability. So I want to look at E1 bar intersect E2 bar, and so on. So each of these occurs with high probability. What's the chance that they all occur? It's also with high probability. I'm changing the alpha, so the union bound tells me the probability of any one of these failing, the probability of this failing or this failing or this failing, which is this thing, is at most the sum of the probabilities of each failure. These are the error probabilities. I know that each of them is at most 1 over n to the alpha with a constant in front. If I add them all up, there's only n to the c of them. So I take this error probability and I get, I multiply by n to the c. So I get like n to the c over the n to the alpha, which is 1 over n to the alpha minus c. I can set alpha as big as I want. So I set it much, much bigger than c. And this event occurs with high probability. So I made a mess here, but this event occurs with high probability because of this. Whatever the constant is here, however many events I'm taking, I just set alpha to be bigger than that, and this event will occur with high probability too. So when I say here that every search costs order log n with high probability, not only do I mean that if you look at one search, it costs order log n with high probability, you look at another search and it costs log n with high probability. I mean if you take every search, all of them take order log n time with high probability. So this event, that every single search you do takes order log n, is true with high probability, assuming the number of searches you're doing is polynomial in n. So I'm assuming that I'm not using this data structure forever, just for a polynomial amount of time. But who's got more than a polynomial amount of time anyway? This is MIT. Okay, so hopefully that's clear. We'll see it a few more times. Yeah?
How do you, when you implement the algorithm, how do you choose alpha? Like, how do you adjust the constant?
The algorithm doesn't depend on alpha. The question was, how do you choose alpha in the algorithm? So we don't need to. This is just sort of for an analysis tool. This is saying that the farther out you get, so we say, well, what's the probability that I'm more than 10 log n? Well, it's like 1 over n to the 10. Let's say it's linear. Well, what's the chance that you're more than 20 log n? Well, that's 1 over n to the 20. So the point is the tail of this distribution is getting really small really fast. And so choosing alpha is more like sort of for your own feeling good. Okay, so you can set it to 100, and then n is at least 2. So that's like 1 over 2 to the 100th power chance that you fail. That's damn small. If you've got a real random number generator, chance that you're going to hit 1 over 2 to the 100 is pretty tiny, right? Because let's see, like 2. So let's say you set alpha to 256, which is always a good number. 2 to the 256 is much bigger than the number of particles in the known universe. So the light matter. So that's actually, I think this even accounts for some notion of dark matter. So this is really, really, really big. So the chance that you pick a random particle in the universe and it happens to be your favorite particle, this one right here or something, that's 1 over 2 to the 256, or even smaller. Okay, so set alpha to 256. The chance that your algorithm takes more than order log n time is a lot smaller than the chance that a meteor strikes your computer at the same time that it has a floating point error, at the same time that the Earth explodes because they're putting a transport through this part of the solar system, at the same time that, I mean, I could go on, right? It's really, really unlikely that you're more than log n. And how unlikely you get to choose, but it's just in the analysis. Algorithm doesn't depend on it. Same algorithm. Very cool. Sometimes with high probability bounds depend on alpha. I mean, the algorithm depends on alpha, but here it will not. Okay. And away we go. So now you all understand the claim. So let's do a warm-up. And this will also need this fact, but it's pretty easy. The lemma is that with high probability, the number of levels in a skip list is order log n. I think it's order log n, certainly. So, how do we prove that something happens with high probability? Compute the probability that it happens, show that it's high. You can know that even if you don't know what high probability means. In fact, I used to ask that earlier on, but... So let's compute the chance that it doesn't happen, the error probability, because that's just a 1 minus. A little bit cleaner. So I'd like to say, let's say that it's at most C log n levels. So what's the error probability for that event? Okay, this is sort of an event. Put it in squiggles just for offset. This is the probability that there are strictly greater than log n, C log n levels. So I want to say that that probability is particularly small, polynomially small. Well, how do I make levels? Well, when I insert an element, probability half it goes up. And the number of levels in the skip list is the max over all the elements of how high it goes up. But max, that's a mess. Right? You can compute the expectation of a max. If you have a bunch of random variables whose expectation is a constant, and you take the max, it's like log n in expectation. But we want a much stronger statement. And we have this Boole's inequality. It says, well, I have a bunch of things, polynomially many things. Let's say we have n items. Each one independently, I don't even care if it's independent, but each one potentially goes up some amount. If it goes up more than C log n, the number of levels is more than C log n. So this is at most. And then, I want to know, do any of those events happen for any of the n elements? So I just multiply by n. So certainly at most, n times the probability that x gets promoted slight mismatch here, greater than or equal to log n times. Okay, if I pick for any element x, because it's the same for each element, they're done independently. Right, so I'm just summing over x here, and that's just a factor of n. Clear? This is Boole's inequality. Now, what's the probability that x gets promoted c log n times? We did this before. For log n, it was 1 over n. For c log n, it's 1 over n to the c. Okay, this is n times 2, let's say, be nicer, 1/2 to the power c log n. 1/2 to the power c log n is 1 over 2 to the c log n. The log n comes out here, becomes an n. We get n to the c. So this is n times n to, n divided by n to the c, which is n to the c minus 1. And I get to choose c to be whatever I want. So I choose c minus 1 to be alpha. I think exactly that. Sorry. 1 over n to the c minus 1. Thank you. Better be small. This is an upper bound. So probability is polynomially small. I get to choose, and this is a bit of the trick. I'm choosing this constant to be large enough for alpha. So the point is, as c grows, alpha grows. Therefore, I can set alpha to be whatever I want, set c accordingly. So there's a little bit of more words that have to go here, but they're in the notes. I can set alpha to be as large as I want. So I can make this probability as small as I want in the polynomial sense. So that's it. Number of levels, order log n. Wasn't that easy? Boole's inequality. The point is, when you're dealing with high probability, use Boole's inequality, and anything that's true for one element is true for all of them. Just like that. Just lose a factor of n, but it's just 1 in the alpha. And alpha is big. Big constant, but it's big. Okay, so let's prove the theorem. High probability searches cost order log n. We now know the height is order log n, but it depends how balanced this thing is. It depends how long the chains are to really know that a search costs log n. Just knowing a bound on the height is not enough, unlike a binary tree. So we have one cool idea for this analysis. And it's called backward analysis. So normally you think of a search as starting in the top left corner, going left and down until you get to the item that you're looking for. I'm going to look at the reverse process. You start at the item you're looking for, and you go left and up until you get to the top left corner. The number of steps in those two walks is the same. And I'm not implementing an algorithm here, I'm just doing analysis. So those are the same processes, just in reverse. So here's what it looks like. You have a search, and it starts, which really means that it ends, at a node in the bottom list. Then each time you visit a node in this search, you either go left or up. And when do you go left or up? Well, it depends what the coin flip was. So if the node wasn't promoted at this level, so if it wasn't promoted higher, and that happened exactly when we got a tails, then we go left, which really means we came from the left. Okay, or if we got a heads, so if this node was promoted to the next level, which happened whenever we got a heads for that at that particular moment, this is in the past sometime when we did the insertion, then we go or came from up. And we stop at the root, where this is really where we start. Same thing. So either at the root, or I'm also going to think of us as stopping at minus infinity. Okay, that's a bit messy, but let me review. So normally we We start up here. Well, we're just looking at everything backwards, and in brackets is what's really happening. So this search ends at the node you're looking for. It's always in the bottom list. And then it says, well, was this node promoted higher? If it was, I came from above. If not, I came from the left. It must have been in the bottom chain somewhere. Okay, and that's true at every node you visit. It depends whether that coin flipped heads or tails at the time that you inserted that node into that level. But, these are just a bunch of events. I'm just going to check what is the probability that it's heads and what's the probability that it's tails. It's always a half. Every time I look at a coin flip, when it was flipped, there was probability a half of going either way. That's the magic. And I'm not using that these events are independent in any way. For every element that I search for every value of x, that's another search. Those events may not be independent. I can still use Boole's inequality and conclude that all of them are order log n with high probability, as long as I can prove that any one event happens with high probability. So I don't need independence between. I need that these coin flips in a single search are independent, but everything else, for different searches, I don't care. So, how long can this process go on? We want to know how many times can I make this walk? Well, when I hit the root node, I'm done. Well, how quickly would I hit the root node? Well, with probability a half, I go up each step. The number of times I go up is at most the number of levels, -1. And that's order log n with high probability. So this is the only other idea. So we're now proving this theorem. So the number of up moves in a search, which are really down moves, but the same thing, is less than the number of levels. Certainly you can't go up more than there are levels in a search. In an insert, you can go arbitrarily high, but a search, as high as you can go. And this is at most C log n with high probability. This is what we proved in the lemma. So we have a bound on the number of up moves. Half of the moves, roughly, are going to be up moves. So this pretty much bounds the number of moves. Not quite. So what this means is that with high probability, so this is the same probability, but I can choose that as high as I want by setting C large enough. The number of moves, in other words, the cost of a search, is at most the number of coin flips until we get C log n heads. Right? Because in every step of the search, I make a move, and then I flip another coin, conceptually. There's another independent coin lying there, and it's either heads or tails. Each of those is independent. So how many independent coin flips does it take until I get C log n heads? Claim is that's order log n with high probability, but we need to prove that. So this is claim. So if you just sit there with a coin and you want to know how many times does it take till I get C log n heads, claim is that number is order log n with high probability. As long as I prove that, I know that the total number of steps I make, which is the number of heads and tails, is order log n. Because I definitely know the number of heads is at most C log n. The claim is number of tails can't be too much bigger. Notice I can't just say C here. Okay, it's really important that I have log n. Why? Because with high probability depends on n. This notion depends on n. If log n is true, anything bigger than log n is true, like n. If I put n here, this is also true. But if I put a constant or log n, this is not true. It's really important that I have log n here, because my notion of high probability depends on what's written here. Okay. Clear so far? We're almost done, which is good because I just ran out of time. Sorry, we're going to go a couple minutes over. So I want to compute the error probability here. So I want to compute the probability that there's less than C log n heads. Let me skip a step. So I'll be approximate and say, what's the probability that there's at most C log n heads? Sorry. So I need to say how many coins we're flipping here for the error, for what this event is. So I need to specify this constant. Let's say we flip 10 C log n coins. Now I want to look at the error probability under that event. Probability that there's at most C log n heads among those 10 C log n flips. So the claim is this should be pretty small. It's going to depend on 10. Then I'll choose 10 to be arbitrarily large, and I'll be done. Okay? Make my life a little easier. Well, I would ask you normally, but this is 6042 material. So what's the probability that we have at most this many heads? Well, that means that 9 C log n of the coins, because there are 10 C log n flips, C log n heads at most, 9 C log n at least better be tails. So this is the probability that all those other guys become tails, which is already pretty small. And then there's this permutation thing. So if you had exactly C log n heads, this would be the number of ways to rearrange C log n heads among 10 C log n coin flips. Okay, that's just the number of permutations. So this is a bit big, which is kind of annoying. This is really, really small. Claim is this is much smaller than that is big. So this is just some math, and I'm going to whiz through it, so you don't have to stay too long, but you should go over it. You should know that y choose x is at most e y over x to the x. Good fact. Therefore, this is at most 10 C log n over C log n, also known as 10. Right, these cancel. There's an e out here, and then I raise that to the C log n power. Okay, then I divide by 2 to the power 9 C log n. Okay, so what's this? This is e times 10 to the C log n divided by 2 to the 9 C log n. Okay, claim this is very big. This is not so big because I have a 9 here. So let's work it out. This e times 10, that's a good number, is we can put upstairs. So we get log of e times 10, 10 times e, and then C log n. And then we have over 2 to the 9 C log n. So we have this 2 to the C log n in both cases. So this is 2 to the log 10e minus 9c log n. Some basic algebra. And so I'm going to set, not quite. This is 1 over 2 to the 9 minus log. So just inverting everything, negating the sign in here. C log n. And this is my alpha. Because the rest is n. So this is 1 over n to the alpha when alpha is this particular value. 9 minus log of 10 times e times c. Bit of a strange thing. But the point is, as 10 goes to infinity, 9 minus log, 9 here is the number 1 smaller than 10, right? We subtracted 1 somewhere along the way. So if 10 goes to infinity, this is 10 minus 1. This is log of 10 times e. E doesn't really matter. Point is, this is logarithmic in 10. This is linear in 10. The thing that's linear in 10 is much bigger than the thing that's logarithmic in 10. This is called an abusive notation. Okay? As 10 goes to infinity, this goes to infinity. Gets bigger. And there's a c out here. But for any value of c that you want, whatever value of c you wanted in that claim, I can make alpha arbitrarily large by changing the constant in the big O, which here was 10. Okay, so that claim is true with high probability. whatever probability you want, which tells you alpha, you set the constant in front of the log n to be this number, which grows, and you're done. You get the claim. It's order log n heads, or order log n flips with high probability. Therefore, a number of steps in the search is order log n with high probability. Really cool stuff. Read the notes. Sorry I went so fast at the end.